Earlier in the chapter, we dealt with ionic compounds. And remember, ionic means that it's a metal and a nonmetal. Metal and a nonmetal. If you look at the periodic table, something from the left plus something from the right. There's a transfer of electrons. Well, this section starts a completely new area. We're going to talk about covalent compounds. Two nonmetals, two things from the upper right-hand corner of the periodic table plus hydrogen. So we're going to have a new naming scheme, and we're going to talk about how these molecules are going to act differently than an ionic compound will. Okay, so this particular section is all about covalent compounds. And covalent compounds, like it says right here, are two nonmetals. So two things from the upper right-hand corner of the periodic table, plus, of course, hydrogen. Now, what makes these unique is that they share electrons. Ionic compounds in the last section had a transfer of electrons. One gained an electron, one lost an electron. And then they were attracted to one another because they were positives and negatives. In covalent compounds, it's a little bit different. You have two elements that want to have more electrons. So to get those extra electrons, they share the electrons. When they share those electrons, those atoms of those elements are going to form molecules. The molecules are electrically neutral. There's no positives, there's no negatives. They're going to be very, very discrete, as we're going to find out, and so they're going to behave just a little bit different. Now, these molecules can be very, very simple. We can start with what are called diatomics. Okay, look at that word there. The prefix di means two. So these are going to be a two-atom molecule where both of those atoms are the same elements. I'm going to tell you some more about that on the next slide. Now, when we form these different compounds, it shows two chlorine atoms, and chlorine is in group 7A, so when you draw the Lewis symbol, it has 7 dots. We know that they want to gain one electron, but here we're going to show they're not going to transfer those electrons. Instead, they're going to share the electrons. So I'm going to draw this little double-headed arrow. Notice this one's double-headed because we're sharing. It's not single when they transfer. So they're sharing that pair of electrons, and they can form a bond in between them. Now, I'm not really happy with how they're showing this as a pair of dots in between those two chlorines. Traditionally, what you'll see is they'll do a dash, and that dash represents a bond. So this is going to represent a covalent bond of two atoms. So we could talk about one pair of electrons. Sorry, I'm trying to figure out if I like how that works. Covalent bond of two electrons. Let's put it that way. Two electrons between two atoms. Sorry. Want to change that terminology just a little bit. So between these two atoms, they're sharing a pair or two electrons total. And we can show that sharing of those electrons as a dash. That dash means two electrons. So let's see here. Oh, at the very bottom, it talks about bonding versus non-bonding electrons. So those electrons that are being shown, the bonding ones are just what they sound like. They're the ones in the bond. We're going to show those with a little dash. Non-bonding electrons are sometimes called lone pairs of electrons or lone electrons. They're the ones up here where we're showing them as little dots. Those are all considered to be non-bonding electrons. And so depending on how many bonding and non-bonding electrons an atom has or a molecule has, you're going to see that it's going to behave just a little bit different. So non-bonding electrons are your lone pairs or your non-bonding electrons. All right, so let's go back and talk a little more about those diatomic molecules. Okay, so we have 7 molecules. 7 elements that like to form these diatomic molecules. There's actually a couple that like to be more complex, like sulfur and phosphorus, but you need to know about the diatomics. So diatomic, again, just means that there's 2 atoms of the same element that like to form a compound. So these 7 in nature, they like to hang out with their closest friend, so to speak. So earlier, in one of the earlier chapters, we talked about the most common elements in different parts of our environment. And we learned that in our atmosphere, in the gases in the atmosphere, the most common gas is nitrogen. Well, nitrogen happens to be one of these diatomics. So nitrogen, when you write nitrogen, you don't just write N, you actually write N2. Because in its standard state, so its most stable form of that element at room temperature and atmospheric pressure, it wants to be in this diatomic molecular form. It's not the only one. Let's see here. We also have oxygen. So when you talk about needing oxygen to burn something, or the oxygen that you breathe, it's in the form O2. There's other forms of oxygen. You could have monatomic. You could have O3. O3 is actually ozone, but you know, ozone isn't the most common form that oxygen takes. Its most common form is O2, so that's the one we're going to talk about. The next one is fluorine. And then we have chlorine, and we have bromine, and we have iodine. So those, whenever you talk about them in nature or in their standard state, you put a 2. Now, when they react, they will separate from one another. They individually react, but while they're just sitting there in the environment, they like to be together. So let's see here. Now, a couple ways to help you remember this. Remember I said that there was 7 of them. And if you look at the periodic table, let's see here, we had nitrogen, we have oxygen, fluorine, chlorine, bromine, iodine. Oh, look, they form a number 7. And not only do they form a number 7 on the periodic table, they're mostly in group, oh, what's this special group right here? Oh yeah, the halogens, group 7A. Oh, that's good to know. So there's 7 of them, mostly in group 7A. They form a 7 on the periodic table, but I've only written down 6. The other one is hydrogen. Hydrogen is also diatomic. Hydrogen is a nonmetal, so even though it's over there on the left-hand side of the periodic table, it is considered to be a nonmetal. And just as a review, the dividing line between our metals and our nonmetals is between boron and aluminum, and then it steps down. Steps down, and then it goes down one more. Again, this one's missing the last row of the periodic table. Other things on this part, if it touches that line, it's also a metalloid. Let me show you one other thing. Let me see. Oh, yay, it erased. I hope it's still recording okay. So here's the 7 diatomics. So there's 6 of them plus hydrogen. Just by looking, could you tell me what phase they're in? A little pop quiz for you. Now remember, depending on what periodic table that you pick up, the colors may differ slightly, and this one is actually different than a lot of the ones that you see. It's the way it goes. The black is still solid, so we have 1 solid diatomic, iodine. We have 1 that's a liquid, bromine. Most times they show bromine as blue. This periodic table does it in red. And then most other periodic tables would have all of the rest in red, meaning that they like to be gases, but they're showing up as blue on this one. So 7 diatomic molecules. So how many of you have siblings, or you know people who are siblings to one another? Whenever they share something, do they share it equally, or sometimes does one of them get that item a little more than the other? I always compare it to a car. Who gets to drive the car more, the older sibling or the younger sibling? Well, it turns out, and this is the way it worked with my kids also, the older one gets to have control of the car more, at least for a time being. Electrons will do the same thing. Whenever electrons are being shared between 2 atoms, occasionally they will share them completely equally with one another. Sometimes I'll use the comparison of twins, but twins don't in real life share things equally. But if they shared very, very equally, that's going to be called nonpolar. So nonpolar, the electrons are shared equally between the 2 atoms. But most of the time, one of the elements likes the electrons more than the other. Whenever that happens, that's going to be polar. Now, an easy way to tell if something's going to be nonpolar or polar, if it's a diatomic where it's the same element, a lot of times we'll say that that one's going to be nonpolar. There are, you know what, I shouldn't talk and write at the same time. Here we go, same element. So if both atoms are the same element, so 2 hydrogens, 2 chlorines, 2 bromines, it's probably going to be nonpolar. There are some cases where different elements will be the same, but we'll talk about that here in a second. If they are different elements, let's write that down, different elements, it's probably going to be polar. And polar referring to the fact that one atom likes the electrons more than the other. And so those electrons spend more time around that particular element. This is due to a difference in what's called electronegativity. I know, really big word. We abbreviated EN, and all that word means is how much does it like an electron. So down at the bottom, we have a view of a periodic table, at least a portion of the periodic table. And you'll see on the far right-hand side, there's one that's in red. Well, on this one, just as a warning, they've removed the noble gases because the noble gases don't want to be in reactions. They don't want to be in compounds. But this one right here that's in red, that's fluorine. Fluorine is a small atom, and it's very electronegative. It has 7 valence electrons. It wants one more really bad. And so it has the highest electronegativity. Now, other than fluorine, the next 2 by it, which would be nitrogen and oxygen, are both extremely high. If you go to the other side, so some of your metals over here on the left-hand side, notice they're really low. Well, that just means that they don't want to have that extra electron. They'd rather give one away. They really don't want to gain one. So polar versus non-polar. So this slide is going to go back to those types of bonds and really emphasize the differences between covalent and ionic. So let's start with a review of ionic. With ionic, we have a metal and a nonmetal. If we relate that to electronegativity, we have something that has a high electronegativity and something that's a low electronegativity. Metals don't want electrons, they want to give them away, so they have very low electronegativities. Now, we actually can show that with these numbers down here at the bottom. That's what those numbers mean. Now, on tests and everything, you won't be expected to know what the numbers are. Just in general, nonmetals, high electronegativities, especially fluorine. Metals, really low. Let's see here, other things. Remember with ionic, there is a transfer of electrons. Let's write that down, transfer of electrons. And when you transfer an electron, something loses an electron. So we have something, such as this sodium, that becomes positively charged. Something else has to gain that electron. It becomes negatively charged. And then there's an attraction between them. Notice that it's showing that with a dashed line. It says, okay, there's an attraction here, but it's not actually a sharing of electrons. They're just attracted to one another. Now, to demonstrate that, if you look down a little bit further, we have a little tug of war. And here we're showing how one team has lost. It gave away its electron, it lost that electron. So that's ionic. Now we're going to go to the other side of the spectrum. The other side of the spectrum is our non-polar covalent. So these are going to share electrons, and they share them very equally. Everything's the same. Usually these are going to be our diatomic molecules, which is actually what it's showing. It's showing 2 chlorine atoms. So here's my 2 chlorine atoms. And if you look at that, there's an area that's shaded in between them. That's called an electron density map, and it tries to show where the electron is likely to be. If you notice, it's very evenly distributed. So this is going to be non-polar covalent. If we look at our electronegativity numbers, they're the same. They're identical to one another. So if they're really close to one another, it's probably going to be non-polar. For us, again, if it's 2 elements, 2 atoms of the same element, it's going to be nonpolar. And if we look at our tug of war, they're equally matched. They're both attracted to the electron, but they both pull with the same amount of intensity. So nonpolar covalent share the electrons equally. And then we have kind of in between that gray area that everyone likes to talk about, we've got the polar covalent. Covalent, they're sharing. Polar, it's unequal. If we look at the electronegativity numbers, they're different from one another. They're not so extreme as the ionic. Usually if the difference between those numbers is like 1.7, they say that it's ionic. This is less than that. So they're still sharing electrons. It just happens to be that in this case, the chlorine likes the electrons more than the hydrogen. Now I can tell that pretty easily by looking at the little picture there. Number one, the chlorine over here is got a lot bigger electron density map around it. The hydrogen is a little bit smaller. The other clue that this one gives me is it gives these little symbols right here. Now I know it's hard to see the symbols, so let me see if I can draw them up here. We have a partial negative and a partial positive. So that's a Greek letter. Its name isn't partial. It's a lowercase Greek letter, and the uppercase actually looks like this. Okay, pop quiz, what's this? This is your delta sign. And delta means change in. Well, if we do a lowercase, these little really funky looking things, that means a partial change. It has a partial positive or a partial negative, a little bit positive or a little bit negative. So those are the three types of bonds that you'll hear a lot about. Now, the interesting thing when we get to especially carbon-based compounds, any of your covalent compounds, they could possibly share more than one pair of electrons. So that's what this slide is trying to show. It's saying that between two atoms, you may have more than one bond, and those are called multiple bonds. So we start with single bonds. That's what we're going to talk about a lot in this class. We show that with just one dash. That's one pair of electrons or two electrons total that are being shared. A double bond, well, we'll show that with two bonds, two dashes. That's two pairs of electrons or 4 electrons total. Our triple bond, oh, there's our triple bond between the two nitrogens. That is 3 bonds or 3 pairs of electrons or 6 electrons total that are being shared. Your nonmetals can do this. The most common one that we end up talking about are some of your carbon compounds, and that is going to get into some organic chemistry. And we'll briefly touch on that subject this semester. All right, so a little question for you for towards the end of this section. This one says the larger the electronegativity difference between adjacently bonded atoms, the more polar the bond will be. Ooh, the larger the electronegativity difference between adjacently bonded atoms, the more polar the bond will be. Okay, so on this one, we're saying they're bonded together, and we're saying the larger the electronegativity difference, so the more the difference is between how much the atoms like the electrons, the more polar the bond will be. This is true. It's very true, unless it gets to be such a big difference that it becomes ionic. But this is just saying, hey, the more difference there is, the more polar it is. Yes, this is true. Another end of section question for you. Which compounds involve metals and nonmetals bonding together? Ionic, covalent, organic, or metallic? Ooh. Ionic, covalent, organic, or metallic. On this one, metals and nonmetals are ionic. The first one's ionic. Covalent is 2 nonmetals. Organic is carbon-based compounds. And metallic is something, I think we'll mention it later on, but we don't talk a lot about metallic. Metallic is, they don't actually form bonds between them. It's just attractions between metals. So that's a whole other section of chemistry. But metals plus nonmetals are ionic. One of the fun things that we get to do in chemistry is we get to visualize what the molecules look like. That's called molecular structure, where we look at the arrangement in space of the atoms that make up a molecule. So one thing that we could look at is we could see for that particular compound which electrons are bonding and which are non-bonding, which are only attached to one atom. We could look at how those electrons are going to take up space. Well, as we try to imagine these, and I'll be the first to admit I'm like three-dimensionally challenged to actually visualize a lot of this stuff when I first started chemistry. It's gotten easier though. There's a lot of different ways that we can try to show this or demonstrate it. The first, down here at the bottom, that's our Lewis structure. So with the Lewis structure, the dashes indicate the bonds, the dots indicate our lone electrons. But the bad thing about your Lewis structures are it appears flat. It appears two-dimensional. You draw it on a piece of paper. But in real life, it's three-dimensional. So we have some different ways to demonstrate that. The ball and stick model looks like this. These are all the same molecule. This is actually looking at water. Now with water, notice that it has a nice little angle here. It's not a 90-degree angle, which the Lewis structure makes it look like. This is actually 109.5. It's actually a little bit less than that. Technically, with water, it's 104.5. It has some lone electrons, which aren't shown with this particular model, but there are some kits that you'll actually be able to see that. But this one, you can hold it in your hands, you can manipulate it a little bit, and it's a little bit easier to see that the molecule isn't flat, it's three-dimensional. The space filling model, this one, okay, let's compare the two. This one gives you a better idea of the size and the better idea that these are actually covalently bonded to one another. They're really close to one another. They're sharing electrons between them. This one, it has some flat areas on it to indicate kind of where the rest of the molecule, the lone electrons are. The thing I like about these is they're actually magnetic, so you can have different atoms come together and you can show the attraction, and we'll find out later on that even though that's not a bond, it's what's called an intermolecular attraction between the two molecules. The molecule won't split apart. That's what makes it a molecule, a covalent bond. But the two molecules can actually be attracted. Okay, they're just kind of fun to play with. They're magnets, come on. So anyway, you'll see these probably again. Space filling model, just through it. Ball and stick. Your Lewis structure is the one that's written with the lines and the dots.